Hello, 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 hello. Hello, everyone. This class, we're going to continue with the computational methods in engineering. And specifically, we're going to talk about interpolation and curve fitting. Okay, so we do a quick recap of last class. Last class, we talked about the symbolic calculation, right? The symbolic mathematics in MATLAB. So we discussed how we can create symbolic expressions, symbolic equations, and how we can manipulate the symbolic mathematics or the symbolic expression, for example, to expand the terms, to find the factors, to collect, which is to rearrange the expression based on certain factors, right? Variables, simplify, right? We can use that quite a lot to sort of simplify, let's say, extended or long expressions, or poly to sim, which is to convert a polynomial term into the symbolic expression, right? We also talk about the solutions. We could use a solve function, right, to directly solve different equations or sets of equations, but also we need to pay attention that here we can only solve the equation that have analytical solutions, right? If it doesn't have analytical solution, then you're going to only find the solution as a root of something, a root of like basically the repeated equation. So under that situation, we have to use some other numerical methods, for example, the fsolve function to find out the solution. Okay, and then the subs function will let us substitute certain values within the expression. We can use the symbolic expression to do easy plotting, right? So it's going to give you a general range of around -6 to +6, but you can also change the range for your plot. We could also use the symbolic expression to do differentiation and integration. So differentiation here, it's actually quite easy. Basically, almost all kinds of mathematical equations have the derivative, right? So you just need to type in the scripts here, and then n here represents how many orders you're looking at, the first order differentiation, second order, so on and so forth, right? And then it can also do symbolic integration, so which is only limited to equations that have symbolic or have the analytical integrals, right? If it doesn't have analytical integral, for example, the log of sine of x plus y, right? The log of sine of x squared. So for these terms, they don't have analytical integrals, which means that you cannot use the symbolic integration to get the integral of the function. And that situation, you have to use some numerical methods to calculate the integral, which we're going to talk about in our next class. Okay, so this class we're going to talk about the interpolation and the curve fitting. So generally speaking, interpolation and curve fitting are sort of similar because basically you're trying to measure or you're trying to calculate values that you have not measured before, right? So interpolation is basically you have two values and then you're trying to find out what's the value in between. For example, here you have two measurements and then it's asking what is the corresponding value of y for this x, right? So there are several methods for interpolation. For example, you can assume that the relationship between the data, all of the data points is linear, right? If it's linear, then basically, and specifically for this case, you can see that when x is 1, y equals 2, x is 5, y equals 10, which means that it's on a y equal 2x line. So it's likely that in between, it's going to also follow this y equal 2x relationship. But this is actually too general or too, I would say, too optimistic. A lot of times, the relationship of the data points are not going to follow these simple linear relationship, right? So you could easily have another data point over here, which is going to completely make your basically the relationship of the data points very sophisticated. Okay, so because of that, there are different ways for us to do the interpolation. The most direct way is the linear interpolation, as I've mentioned before, right? So for example, we could have two data sets, right? So X is from 0 to 5, 0, 1, 2, 3, 4, 5. And then here are the y value. Let's just type in the values here. And then let's make a simple plot. Okay, so this is our data points, right? So you can see that it starts from here, actually. And then we can also sort of maximize our limit a little bit. Then -2 to, let's say, 6 or 7. Okay. Well, so instead of using the command window, let's just create a script. So it's class, it's a 14. Right. So first interpolation. Linear interpolation. Okay, so this is our x. Then we made the plot of x, y, and then circle as a marker. And then we can set our x limit would be -1 to 6. And we can also set our y limit. Let's say -2 to 17. Okay. All right, so this is our plot. So you can see that, well, it looks like these data points align on a same line here, right? But then there are up and downs surrounding this line here, right? So it is actually safe for us right now to actually assume that the relationship between the data points are linear. But we're going to talk about the linear relationship or the curve fitting later on. So now the problem is, well, how do we find out the data points in between, right? So here, basically, if we use the interpolation method, we're assuming that the data that we measured here are accurate. They're all accurate, right? So under this situation, for example, if you want to find the value of x equals 3.5, which is here, you assume that between each data point, they follow a linear relationship, okay? So you can directly connect the lines here, and then at 3.5 is just going to be the average of these two data points, okay? So what it means is, let's say we save our script here, right? So you could do y equals, or let's say y1 equals interp1. So the reason why we use interp1 is because this is 1D interpolation. Okay, so linear interpolation. You could also have 2D interpolation where you have x and y being in certain range or certain match, and then you have the z value. You're trying to interpolate the z value. But here it's just going to be one-dimensional interpolation, 1D interpolation. So you're just going to use that, and then you have x, y, and then we put in the x value, which is 3.5. Okay, so then you could run this again. You can see that y1, which is in between, is going to be 4. It's going to have a value of 4. Okay, so you can see that we could actually interpolate just one point, but at the same time, we could also actually put in an array as long as the array is within this data stream here, right? So let's say we could define this new x being 0 to 0.2, 0.5. So to 5. So we're trying to create a finer mesh, finer grid, right? So now you're, because originally it's separated by 1, right? Now we're trying to separate them by 0.2. And then the new y will be interp1, x, y, and new x. Okay, so this is a new y. And then let's do the plot. Okay, plot x, y being using a circle, and x new, or new x, and new y being the dots. run this again. And you can see how the plot looks like, right? So here we can also add in the legend, right? So original and interpolate. Original, interpolate. All right. So you see originally we have 6 data points, right? Shown as the circles here. And then the interpolated data are actually going to follow the linear relationship, right? This is linear interpolation. Okay, so you can see that it's just a straight line connecting the 2 data points, right? So this is the interpolated data set. Okay, so this is linear interpolation. And you may say that, well, linear interpolation seems too sort of too naive, right? Because clearly the data points should be following some relationship here, but it shouldn't be linear, because if the data points that we show, the original data, are real, it means that at least it should be following some certain curvature here, right? Instead of a linear relationship, right? So still remember here that we're talking about real data, right? So the accurate data. If this is indeed the data that we measured, and then we can ensure that this is 100% accurate, then to do the interpolation, we assume that these data points are real, and then we basically connect these data points and with some certain shapes of lines. Right here, we're connecting them by straight lines. So because of that, there are other ways to conduct the interpolation. For example, you can use the cubic spline interpolation. So what the cubic spline interpolation means is that now it's using a third order polynomial. So we know that second order polynomial is just involve x squared, right? So here it's using third order polynomial, which can have certain curvature in the polynomial line. And then basically the way you can do the interpolation is just still use the interp1, but then specify that this is cubic spline interpolation, and specify that this is using the spline method, the cubic spline method. So CCLC layer. I'll also put it over here. Okay, so we don't need to make the plot over here. And then we just need to specify that here it's spline. Okay, so now we can run this function again. So you can see that now it start to have these sort of the curvature that connects the dots together, right? Connect these data points together. So again, there's a difference between the interpolation and curve fitting, right? So where here, this is not a curve fitting. This is just an interpolation of data points between the measured accurate data, right? So we're not fitting the data points by a line here. And we're just connecting all of the data points with certain algorithm. Okay, so you can see that the cubic spline interpolation will give you more smoothed lines over here. And then basically, the other thing we should pay attention to is that because this is using third order polynomial, so it needs 4 terms, because there's x squared, x cubic, x second to the order of 2, x to the order of 1, and then there's a constant. So it needs at least 4 data points to model the behavior of the data. And in fact, MATLAB has a series of these interpolation methods. For example, we talk about the linear, the spline, right? So there's also this nearest method. There is this, let's say, p-chip method, which is shape preserving piecewise cubic interpolation. There's this cubic method, which is the same as a p-chip. And then this V5 cubic, which is cubic interpolation from MATLAB 5, which does not extrapolate and use spline if x is not equally spaced. Okay, so we can just quickly plot all of these together and just give you understanding, right? So some of these will be the same as the notice as the table indicates. Interpolation. We can copy everything here, and then So new Y spline. Linear. So, okay, so you see, there are actually different methods, right? So we can use the nearest over here, and then we can try, for example, the P-chip method. Chip. And then let's try just the last one, V5 cubic. So these are different ways to sort of show or to interpolate the data. And as a matter of fact, we actually don't need to put the name here. We can just do uh, one, 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 two, five, four, four, three, two, one. Okay. So then we can do Y1 using the dots here. Let's just keep on using the dots. It's just in the legends um, we'll specify which type of interpolation it is. Okay, Y2, Y3, Y4, we need a Y5. Okay, then finally, legend. So it's going to be linear, spline, nearest, feature, and 5 cubic. Okay. So instead of using 0.2, let's use 0.1. So it's going to be a finer representation of the data. Okay. So this is our final plot. Okay. So you can see basically the red data points are the circle. Oh, I think I made a mistake. So mu x, okay. So yeah, I think there should be another thing. This is original data. Let's make the plot again. Yeah, so there are in total 6 different types of data. Okay, so the circle here again is our original data. The linear is the red ones. They're shown here, right? They follow the straight line. The linear relationship spline, you start to have the curvature, right? So these are the yellow data point. The purple, the nearest, you see the nearest actually, it just gives the same value for the data points in between, right? So if it's between 0 and 1, right? So if it's below 0.5, then it just takes the nearest value compared to the original data. If it's larger than half, right, it gives the nearest value of the next y value, okay, which is sort of like very simple interpolation, okay. Then p-chip, right? This is the green data points. You see some curvature here, but it's not as big of a curve compared to the cubic. The cubic spline method, and then there's also this V5. So there you also have some curvature here. It's different types of curves basically for interpolating the data. Okay, so then depending on the use of your function, let's say different types of interpolation, you can choose your own method to do the interpolation. Okay. So here, this is the hands-on example. So basically here you have some internal energy value that's of the steam, right? Internal energy of superheated steam at 0.1 megapascal, which is 1 atmosphere. right, as a close to Y atmosphere as a function of temperature. So you can see the temperature of the steam can go up by go up to several hundred degrees Celsius, and then the internal energy will be much higher. So use the linear interpolation to determine the internal energy at 215 degrees Celsius. Use linear interpolation to determine the temperature if the internal energy is 2600 kilojoule per kilogram. So then let's do this superheated steam. Okay, so we know that the x value and the y value here, we just need to do a linear interpolation, right? So x is going to be 100, 150, 200, 250, 300, 400, 500. Okay, so this is our x value. Then we need to find our y value, 2506. So to avoid wasting the time, I'll just type in the first three numbers. Okay, I will just do an approximation. 2660, 2733, 2810, 2970, 2130. Okay, so then to do the interpolation, well, the internal energy, let's say IE, is going to be interp 1 x y, and then just give it the temperature, which is 215. Okay, you run it. This is going to be the internal energy, and then you also want to find out the linear interpolation. Find out the temperature if the internal energy is 2600. So it's the same thing. We can just do, instead of x and y, we can do yx. 1 yx, and then 2600. Okay, so then you can find out the temperature. So here, then we may have a problem because now we're doing the linear interpolation, and then we're assuming that actually it follows the relationship of having a larger x will lead to a higher y, right? The higher internal energy. So what if it has a U shape, right? So if it's a U shape, then it could be that on both ends, you can have a higher value, but then it might give you two different x values, right? So we can also test it out. So for example, instead of having 2600, right? So let's make here be 2700, right? So you see that now, when even at lower temperature, you could have a higher internal energy, right? And then it sort of follow this U shape here. So what result are we going to get? So if we run it, you can see that it still has the same 157, right? So, but instead, let's say that we just choose the first three temperatures. So this is where we need to be careful, okay? So let's just comment this out, and then let's just take the first three temperatures. So if you take the first three temperature, right? So then I run temperature equals 2600, right? So let's see. Yeah, still the same temperature, but now let's just choose the first two. So if you choose the first two, we cannot do the interpolation here anymore. And then it turns out the temperature is 145. So it really depends on what the relationship of your data looks like. If it has a U shape, then when you do the interpolation to try to find out the original temperature or original variable, then you need to be careful. It's always good to make the plot of the data first and then find out what's the relationship of the data so you can do the interpolation. Okay. So this is the example, and then here's another example. Create an x and y vector represent the following data. So we can create the x and y plot. So use linear relationship interpolation to approximate the value of y when x equals 15. So we can just do interp 1, right? So let's put it over here. XY. Example. So here we have X being 10, 20. So if that's the case, then we can just do 10, 10, 100. Okay. So then we can create the Y array. That is 23, 45, 16, 82, 101, 140, 7, 198, 200, 220. Okay. So the first problem wants us to plot the data in the XY plot, so which is plot X and Y. Okay. So put the clear CLC over here to avoid the confusion of the program. So this is our plot. So we have X being the x-axis, Y being the y-axis. So is it 220? Yeah, so you see that at 80 and 90, so the data is a little bit off, right? So theoretically, or it looks like it's actually following this 2-to-1 ratio, but then when the x value is large, then you might be having some uncertainty in the data. Okay, but it's okay. This is what we measured, right? So now we want to use a linear interpolation to find out the y value when x equals 15. So you just do interp 1, x, y, 15. Okay, so you see the result is 34. So use cubic spline interpolation to estimate, right? So then we can do y2 and then spline. Okay, so it's different, right? And then use the linear interpolation to approximate the value when y equals 80. So if y equals 80, right? So then you will do the other way of interpolation. So x1 equals interp 1 y x 80. Okay. So this is x1. Cubic spline interpolation. Okay, these are just practice. You can see basically they're going to generate you different results, right? So different x values. Use cubic spline interpolation to approximate y values for x values evenly spaced between 10 and 100 interval of 2. Okay, so now cubic spline method. So then x, let's see, just use the same method. New x is going to be 10 separate by 2 until 100. And then we generate new y being interp 1 x, y, new x, and then spline. Okay, so then finally, plot the original data on an XY plot as data points not connected by a line. Also plot the values calculated in exercise 6. So it's kind of similar to what we had before. So plot x, y with a symbol of circle and then x or new x, and then new y, and then let's use dot. Okay, legend. Original spline. Okay, so this is our data. So you see how the cubic spline method is connecting the lines by these curved lines, right? Although here it looks quite linear, but then when you got to here, right, you start to have these curved lines connecting the points. And then this is how we do the interpolation, right? So if it's linear interpolation, then it's just assuming that the relationship between the two dots are linear, and then you do the linear calculation here. Okay, so this is interpolation. So actually, if you think about the way we interpolate the data, we can only interpolate the data within this X range, right? So we can't really predict what's happening outside this line, outside this function, okay? So if you want to predict outside the original range of the x, then that's called extrapolation. So extrapolation basically predicts outside, right? So let's say that this is our original data again. So extrapolation. So you have, let's say, the same thing here, x and y. And then, for example, if it's talking about a value, if it's talking about the value of x equals 6, because you know original x is only in the range of 0 to 5, right? If it's in the range of at the value of 6, right? So you could also use either linear extrapolation or cubic spline extrapolation. So different ways to extrapolate the data, right? So you'll see here, right? So then you can have the data here. But as you can see, when x equals 6, right? So different ways of doing the extrapolation is going to lead you different results. So the reason being, let's see if we can still show the plot over here. So this is a spline method. We're showing all of the data. You just run data over here. So you can see that basically, if it's linear interpolation or linear extrapolation, you're just going to extend this value further down, right? So then at 6, if it's linear, then it's going to be negative value. But then for the cubic spline method, which is the yellow dots, you can see the curvature here, right? So theoretically, if you extend the line here, it's going to curve back, which is why it's going to give you a positive value. Right. So that's why if you run this script here, right, you see for the linear method, you get -2, and then for the cubic spline method, in terms of extrapolation, you get 3. So that's why it's not recommended to do extrapolation based on data you have. Okay. So especially when you have higher orders of let's say the extrapolation, then you could have very, very different results. For example, you could even fit the data with a 4th order, 5th order, then it could just skyrocket, right? Shoots up so large, it's making the data not realistic. Okay, so MATLAB can do extrapolation, but extrapolation is not recommended. Okay, so we have been using this function of interp1, but we also mentioned that we could actually do into the interpolation also. So for example, you have the range of x equals 1, 2, 3, 4, and y being 2, 4, 6. And this is the z value, right, corresponding to different x and y values, right? So then the question could be, when y equals 3 and x equals 1.5, what is the value? Of course, you could do the interpolation one by one. You could do a linear interpolation between these two, right, to first get y equals 3, and then do another interpolation between 1 and 2 to get the results. But actually, you could just directly use this script here. So it's going to be 2D or multi-dimensional interpolation. So we just need to do y equals 2 to 6, x equals 1 through 4, and then give it a z value. So to save some time, I'll just make the z value being a random number, right? 3 rows and 4 columns. Okay, so then you can just simply do interpolation 2 of x, y, and z, right? So x, y, and z, and then give it 1.5 and 3. So if you run the, let's say, interpolated, right? So if you run this function, you can see that the interpolated value is 0.5. Okay, so basically this is a 2D interpolation, and I think you can also choose these different methods: spline method, right? Linear method. So the default is a linear method. You can use for example, the spline method and see what you get. Okay, so spline method is going to be different. So I don't think we have to use a double quotation sign. Let's see. Yeah. So the reason why it's changing is because we are generating new random number every time. Okay, but you don't have to use double quotation sign, just single quotation sign is good. Okay, so this is multi-dimensional interpolation. So next part is the curve fitting. So as I said earlier, curve fitting and interpolation are different because you may think that here what we have done is fitting the data with certain curve, but here we actually assume that the data we collected are accurate. But the thing is that curve fitting, we assume that the data we collected is inaccurate, which is why we need to find out the underlying relationship, which is to basically fit certain data, right, with certain curves. And then after we get the equation for this data set, then we can predict the value at unknown locations. So it could be, for example, we're still talking about this case here, this original cubic spline interpolation, right? We're comparing different interpolation methods. So if you look at the original data, right, which are the circle ones, you could easily think of a linear interpolation, which is going across these lines, but not touching, going across these data points, but not touching any of the data point, right? So it looks like it's a linear relationship, right? So then it's also going to minimize sort of the error between the line and the data points, right? So this is the underlying mechanism. And then with this equation, we can further calculate or predict the value between the data points, right? So basically, this is where the difference between curve fitting and interpolation is. Interpolation assumes that all the data points are accurate. Curve fitting assumes the data points are inaccurate, right? There's uncertainty, and we're trying to find out underlying mechanism among the data points. Okay. So of course, the most simple one is the most simple one is a linear regression, right? So the linear regression is going to be basically connecting, or not connecting, but finding out the underlying mechanism with a linear line here, right? So basically, for example, this is still our original data, right? You could simply come up with a line saying that, hey, what if the slope is just 15 divide by 3, right? So basically just using this relationship here, right? Assuming that it's going across a line here, and then, for example, delta x divided by delta y, which is 15 minus 0 divided by 5 minus 0, which is minus 3, and you can create this line here. But the thing is that after you create this line, you can see that there is actually a difference between the data and the fitted line, right? So this is the error, right? This is the error between the fitted line and the original data set. So the goal of the regression or the curve fitting is sort of to minimize the error between the data points and the fitted line. Okay, so basically this is a classical problem of the optimization. So I think you probably have also learned this from your statistics class or probability class. So there is a solution to this problem by using the least squares method. So what the least squares method is that we want to calculate the summation of all the errors. So if you think of the error, then it's going to be the deviation of the data point and the line, right? This is error, but this is at this point. You have the error at other points too. So, and the other thing is that if you have the error, which is, for example, the line value minus the data point value, line value minus the data point value, but then there are also scenario, for example, the data point could be higher than the line value, right? So then you end up having both positive error and negative error. And you don't want to add those errors together because they will cancel out and saying that there's no error, right? So that's why we need to do the square error, least squares error method, right? So squared error, and then add all of the errors together, or the error squared together, right? So whenever the squared error summation is the smallest, it's the least, right? So we know that this should be the solution that fits the line or fits the data point. Okay, so it turns out that in terms of the least squares method for linear regression, there is an analytical solution. So for example, if you have a data set, right, a set of X and Y, then you're trying to fit the X and Y data points with the equation of Y equals A plus B X, right? So then A and B can be calculated in this way. So A is equal to the average of all the Y value multiplied by the summation of X value squared minus average of X multiplied by these terms together, multiplied, so sort of the dot product, right? And divide by the summation of X squared value minus N, how many data points you have, X average squared. So B is this term, B is the term in front of X, right? A is the constant term. Okay, so then basically here you get these different terms, and then you can calculate, you can predict what is the X and what is the equation that fits all of the data. So let's say that we just quickly test this function here, right? X equals these terms, right? Y equals these terms. It's linear regression. So we should have the title of curve fitting. But first, it's linear regression. And then these are our X and Y's. And then in order to get the slope and the intercept of this fitted linear line, we can just use the function of polyfit. So polyfit X and Y. And if we fit it with the first order equation, which is a linear line, right? So if you run it, poly it should be double. Okay. Polyfit. Looks like I don't have this function here. Polyfit. CF2. Okay. Spell the wrong thing. It should be polyfit, not ployfit. Polyfit. Okay, so these are our coefficients. So basically here, this is a coefficient for the constant, for the x term, and this is the coefficient for the constant. So here, this is slope, and this is the function, right? This is the intercept. Okay, so how do we show the data? So you can just show the data by using let's see. Okay, so let me see. Polyfit. I think we could also use the polyval. Right. Yeah, so we could just use the polyval, so which is a new y. Y being polyval of, let's say, name these as coefficients. And then we give it coefficients and then the x value. Right, so now we can make the plot of x, y with the circles, x, new y. Let's just use the lines. So now you can run it. So you see, this is our results after the curve fitting, right? So you can see that this is actually not the interpolation, right? Interpolation is just using the known data set, connect them together, and then find out what's the value. So curve fitting is trying to fit a line through all of these data. So this is the underlying mechanism. And now with these coefficients, you can find out or calculate what is the value in between, estimate what's the value in between. Okay, so let's get back. All right, so these are the coefficients. As I said, there are analytical solution, right? There is an analytical solution for calculating A and B. So here, specifically, we're talking about B being minus 2.9143, A being 14.2857. And how did we calculate that? We just plug in these sets of equations, right? So basically, A, the constant intercept, should be this term, and then the slope should be this term. But is this indeed the case? Let's just do a quick calculation. So for example, now let's calculate A, which is the intercept, right? So then we're talking about the mean value of Y multiplied by the summation of X squared, right? So X dot multiplied by X, right? This is summation. And then minus mean of X multiplied by the dot X or Y, right? So dot X, Y is a summation here, right? So then we divide that by the, so this is how we make a line break, right? So you just put 3 dots here and then 3 dots here to make it, okay, we put a bracket, summation of X dot multiplied by X. Let's see. Let's still use the same line. Okay, minus n, right? So length of X multiplied by mean of X squared. Okay, so we can calculate n is not length. Okay, so you see A 14.2857, right? This is the analytical solution for the intercept regarding this linear interpolation. And we can also calculate B. It's just going to be a little bit sophisticated here, right? So then we can use what we had here, dot xy minus mean of X multiplied by sum of Y divided by sum of X minus length X multiplied by this term. Okay, so you see B, which is our intercept, minus 2.9143. So as I was saying, these are just the analytical solutions, analytical expressions for the terms regarding the linear interpolation. Right? This is A is the intercept, B is the slope. Okay, so another thing that sort of remind us regarding the calculation of the linear interpolation is the linear regression is that earlier when we introduced the matrix calculation, right, we said that there could be problems that are over-defined, right? So what the over-defined equations means is that, well, theoretically, you have 3 unknowns. You just need 3 equations to quantify the 3 unknowns, right? Specifically for matrix calculation, these 3 equations are linear equations, like x, y, z, right? So theoretically, you could just use 3 equations to calculate x, y, and z. But in engineering, a lot of times we have extra equations. So now think about the case for our linear regression, right? So theoretically, if our measurements are really, really accurate, right, the same value as expected, we just need two data points to come up with this linear interpolation, right? The linear regression. But the thing is that our measurement is always subject to error, right? So that's why we have to measure at different points, right? So that's why we could add one more equation. And then we said that for overdefined problems, we could use the left division method, right? So basically you create the matrix of A, and then you have the B, and then just A backslash of B to calculate X and Y, okay? So can we do that here? Actually, we can, right? So if you go back to these equations again, basically here we're substituting the X values with 0, 1, 2, 3, 4, 5, and then the result will be 15, 10, 9, 6, 2, 0, right? So we're trying to solve for what is A and B. So similar to here, we're trying to solve for what is X, and Y. So we could rearrange these equations. So it's going to create us 6 different equations, linear equations, right? And then the terms coefficients in front of A is always 1. The coefficient in front of B is 0, 1, 2, 3, 4, 5, okay? So then what we could do is we can create this matrix being 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. Okay, so this is our matrix. And then our term, right? So the solution on the right-hand side is going to be the y value, which is 15, 10, 9, 6, 2, 0. Okay, remember that. And then to calculate A and B, right, sort of to calculate X and Y, right, we could just use, let's just do, let's say the final, it's A backslash of B. Okay, we can do the calculation. Matrix dimension 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Oh, okay. So here we should use semicolon. Okay. So these are our X, right? So it means that A 14.28, B negative 2.9, right? So that's why earlier when we say that we use the back or the left division method to solve for the linear solve the over-defined equations, we're using the least squares approach, right? So it's the same thing, least squares approach. You can see this linear regression problem as a problem that's solving for a set of linear equations, okay? So here we're talking about different ways to solve for A and B, right? So we can use a polyfit directly give you the coefficient. We could use the analytical solution, right? Calculate the two terms for the linear equation, right? We could also use the left division method to calculate the two terms, basically the slope and intercept for our linear regression or the fitted linear line. Okay, so to make the plot, as we said, we could use the polyval function. You have the two coefficients or as many coefficients as you want. Here we're trying to fit it with a linear line. You can also create a, let's say, second order, third order, fourth order, so on and so forth, right? We're going to show that later on too, right? And then find out what is the actual value that make the plot. Okay, so the other problem is, for example, here, a lot of times when we're trying to create a linear regression through 0, right? So you can see that basically if this is our result, right? So this is our measurement. Let's make C clear. And let's make X being 0, 0 to 10 to 50, and Y being, which is our force, right? 0, 24, 38, 64, 82, and 90. Okay, so basically this is talking about the force on an object when you have different velocities, so sort of the drag force, right? So theoretically, we know that when there's no velocity, right, no wind velocity, the force should be 0, right? So when velocity gets bigger and bigger, then the force is getting bigger and bigger. So then We could again do the polyfit coefficient being polyfit x, y, 1. And then we could do new y being polyval x. And then we can make the plot. Just copy everything here. Paste it over here. Okay, so this is our fitted line, right? So you can see that our data is over here, right? And then our line is over here. But then this fitted line is not going to be what we want. So the main thing is because this is telling us when there's no wind, there's still some force being added onto the object, right? Which doesn't make sense because we know that when there's no wind, no relative velocity, then there's no drag force, right? So the force should be 0. So how should we force this slope or force the intercept to be 0, right? So we cannot directly make the intercept to be 0. So for example, let's show the coefficients, right? So this is our coefficient, right? Basically, first, this is the intercept, the second is the, first is the slope, and second is the intercept, right? So we cannot directly make the intercept to be 0 because otherwise it's going to just drag everything down, right? So if you want to do the plot, right? So you could basically make, let's say, make a new y, right? So let's try to make the intercept to be 0. So what you have is going to be 1.8571 and 0. Let's use dot this time. New y 1. Okay. So you see, if we just directly make the intercept to be 0, then you're going to fit the line in this way. In this way, which is not going to get close to all of the data points, right? So the least mean square is going to be bigger. So under this situation, how do we find out the slope that can give you the least squares? Okay, so this again goes back to the calculation for the overdefined, basically the overdefined sets of equations. So now we know that there's no A term, right? So there's no A term, it's just B here, right? So then you can just do B of X, right? Equals the Y here, and then this is an overdefined problem, right? So then you can just define this A, this new A matrix, only being the X, okay? And then the B term is just a Y. And of course, I think we have to transpose it. Okay, so then the slope is going to be A left division B. Okay, because now we know that the A term is 0. Okay, so it's again an overdefined problem, right? We converted the overdefined problem and then use the left division method to find out what's the slope. Okay, so now this is the new slope. All right, so then we could make this new y here, y2 being 1.9455. Okay, so this is our new one. Let's see. Those are our figures. And then make the plot. Okay, so this is original data, right? And then this is the original fitted line. Okay, so we can set that intercept to be 0, and this is the yellow line is what set the intercept to be 0, but you can see that this one basically have a higher least squares, right? So this purple line is the one that will set the intercept to be 0, but still has the least squares value. Okay, so we convert that into an overdefined problem and then use the matrix method, left division method to fit the data. Okay, so then this is linear regression, but you could say that, well, a lot of times linear is not sufficient. Right? You could also have higher orders, right? So the next commonly used method is the polynomial regression. So polynomial regression is going to be very similar to the linear regression in terms of the code. You just change the order here. You can use second order, third order, fourth order, so on and so forth, right? So for example, let's say we just copy the scripts over here, polynomial. Okay, so instead of using 1, let's use 2, and then we should be using the data here. Okay. So then these are our coefficients. So if you make the plot, there's the plot over here. Okay, but if you make the plot, it's going to look like this. So the line is a little bit curved, right? This is not a straight line anymore. And then you can even try, let's say, change it to 3. So you can see the fitted line is going to have sort of a bend over here, right? So a small bend over here and a small bend over here. So the other thing we can try is instead of using x, we can use a finer x, let's say new x, being 0.1 to 5. Then let's use new x. New x and new. Instead of mu x, new x. Okay. You see this is a third order polynomial regression, right? So you're starting to see the curve here. You can even use higher. Let's use 4, right? 4, you start to fit the data even better, right? If you use 5, right, you can see that the fifth order almost can connect everything, right? 1, 2, 3, 4, 5, 6. Let's try sixth order. I don't know if sixth order can still run. Right? Can still run here. 7. Let's try 10th order. Right? You can see that 10th order is starting to get a little bit crazy, right? So trying to fit the basically still minimizing the error, but now you're seeing a very huge spike over here. So now you can imagine if we do an extrapolation using this fitted line here, you can see that when it's x taking value of 6, it might go to minus infinity, right? So then this basically reflect the problem of how do we fit the data, right? So for example, this is basically showing what we have done earlier, right? Second order model, third order model, fourth order model, fifth order model. So the fit is getting better and better. Right, let's try fifth. So this is our plot, right? So it's the same as what's provided here. Okay, so it's getting better and better, but then we want to avoid the problem of overfitting, right? So for example, this is our data, right? So you just look very irregular, right? But by using this overfitting, you might be getting a cat out of it, right? So there's always a extent of how much fitting we want to do. And normally, I would say people will typically use first order, second order, and third order. They won't go further high up because, as you can see, when you have higher orders, then you will have a lot of, let's say, extreme fitting methods that is going to make your result or make the fitted line look very strange. Okay, I would say we'll only go up to the third order, but most of the time, I think is second order is sufficient. And most of the time, of course, is first order. It's a linear regression. Okay. So yeah, so here it's also saying that you could create a for loop instead of just typing in the value here. You can just create a for loop and directly make the plot. Okay, so we're going to skip that over here, but you can see just create a for and then change it, rotate it, or iterate it from 1, 2, 3, 4, 5. Okay, so here this is another example. Example 13.3. So it's talking about the water in a culvert, right? So basically it doesn't have a uniform shape, uniform cross-section area. So that's why the flow and the height of the water inside is not going to be a linear relationship, right? A direct relationship. So obstructions might influence the flow, friction is important, and so on. So a numerical approach allow us to fold all those concerns into a model of how water actually behaves. So this is the height of the culvert, right? This is the flow. So it wants us to compute a best fit linear, quadratic, right? Second order, right? Cubic equation for the data and plot them on the same graph. Which model best represents the data? Linear is first order, quadratic is second order, cubic third order. And also include a linear model that force through zero, right? So there are 4 different models. We have run through these earlier. So let's just make the X and Y X and Y arrays first, right? 1.7, 1.95, 0.6, 2, 4.04, 1.24, 0, 0.6, 3.6. Okay, so these are all X and Y values. Okay, so first order, we just did it, right? So we can just maybe make it over here. Right? Name it coefficient 1, right? First order. And then it's coefficient 1. And let's name it Y1. So it's easier when we make the plot. Okay. X, Y1. And then we also need to make the second order, the third order. 2, 2, 2. And then 3, 3, 3, 3. We also need to calculate the slope that is just that forces all of the fitted or forces the linear line to go through the 0 and 0, because we know that when the height is 0, the flow is 0. It should be 0, right? So then slope is, let's try if we can directly use X backslash Y. X backslash Y. No, we cannot. So it has to be X transpose and Y transpose. Okay. Yeah. X transpose backslash Y transpose. Okay. So then let's make that Y0, because we know this should be the accurate line, sort of, because we know that when the flow is 0 or the height is 0, flow is 0. So it should be slope 0, X. Okay, so let's now make the plots. 2, 3, 4. Oh no, only 2, 3. All right, 0, 2, 5, 3. Legend. Original data. And then we fitted this linear, goes through 0, linear, second, third. Now we'll make the plot. All right, so this is how the fit looks like, right? So of course, I think we should also make our the polyval a little bit smoother, right? Which means that it's going to be like having more data points in between. But then you can generally see how the data looks like. This is our original data, right? At 0, right? So then we could fit it by a linear line that goes through 0, runs through 0. But then you can see that because this data point creates too much of an error, right? So it doesn't fit the data really well. And then you could also have the linear line, which is over here. It doesn't make too much sense because you don't have a negative flow, right? Negative flow doesn't make sense. Second order, right, it's going to look like this, right? I would say the third order fits data a little bit better, right? So of course you can create even higher orders, but uh, as we know, we should know that the data is always the measurement data is always subject to errors, right? So we cannot say that it's the purely accurate data. So in that case, if the error, I mean, if you use a higher order of the fitted line or the curve fit, you might be influenced by the error that give you sort of the crazy or very strange higher order of curve fit. Okay. So there's another problem, another example, the heat capacity of the gas, the amount of energy necessary to warm up 1 degree Celsius depends on not only the gas, but the temperature as well. This relationship is commonly modeled with polynomials. For example, consider the data for carbon dioxide. This is the carbon dioxide temperature, and then here's the heat capacity. It looks like the higher the temperature, the higher the heat capacity. Right? So use MATLAB to model these data as a polynomial, then compute with these combined obtained or compute with those obtained from model published by this person. Okay, so this is sort of the equation. Okay, so then we can extract the data first. So if we type in the value, it's going to take quite a lot of time. So what I'm going to show you is to use Excel to get the data out. So if you go to our textbook, right, so this is our data. I think I also sort of showed this earlier. So if it's a PDF, then you can select all of these data. So just copy and then go to an Excel. So here you can paste. You can see that basically the first one is getting copied, right? The second one and then the ones below, they sort of paste it together. Okay, so we can just first bring these data points here, right? These results here, and then we can select, go to data and text to columns. So delimited by space. So in this way, it's going to separate the data out. And then let's bring the data back to here. Of course, you need some formatting, right, to remove the empty lines in between. Delete. So this is our data, right? So we don't need to type in anymore. We'll save you some time, right? So this is the X and this is the Y. So let's just put it in our script. So this is sample 13.4, right? So we have our X being, well, let's say temperature, right? So temperature being this column here. Just to look a little bit elongated, which is what I don't really like, but to save some time, let's just do this away and do it this way. Or let's transpose it. It's okay. All right, so we can transpose. All right, so let's just copy in this way so it looks a little bit nicer. P, and then so copy CP. Okay, so these are the extracted data. All right, so now we're trying to fit it by a second order polynomial. So how do we do that? Coefficient being polyfit TCP, right? And then we can basically just calculate the polyval, right? So CP new, let's just make temperature also new to be new. So polyfit, and then we're trying to fit a second order or third order polynomial, right? Third order polynomial. So yeah, let's just use CP new being polyval coefficient, and then T. And then let's make the plot. T, CP, T, CPU. Okay, so new result and then show data. So this is how it looks like, right? X-axis being temperature, y-axis being the CP third order polynomial, right? So if you want to show the coefficient, this is how it looks like, right? So coefficient here being C clear. Okay, so the coefficient here being 0, let's see, 0, 0. So these are very, very small values, right? So yeah, let's see here. So basically, you can bring this data from the worksheet here, right? So then this is the coefficient in front of the third order, second order, first order, and zeroth order. So you can see that actually it's a little bit off compared to the result over here, but it's close enough, right? The result are close enough. Yeah, so basically this is how we can do the curve fitting with higher order polynomial. So the last thing I want to show is the interactive curve fitting tools. So here we have been using the polyval, polyfit, right? Mainly the polyfit to do the curve fitting. But it could be that our result, our data, doesn't follow these polynomials, right? Most of the time, it could be polynomial. I would say most of the time it's linear, right? So then it could be higher orders of polynomial, but then it could also be that we're talking about a normal distribution, right? So let's say we collected some data and then it looks like it's a normal distribution. How do we find out the average and the standard deviation of normal distribution? So under that situation, we can just use these interactive curve fitting tools, right? So then the first one is still, I would say, the polynomial method, or let's say still the polynomial method, which is, let's say we can do, since we already have temperature and CP, let's just make the plot T and CP. Okay, so this is our data. Okay, so then in this plot, you could click tools and then go to the basic fitting. Okay, as the name suggests, right? Basic fitting is just going to be very basic. You cannot assume other types of like other types of regression, other types of fitting curves, right? So here we're still dealing with the polynomial. Okay, so you could fit it by linear. If you click linear, it's going to show you the linear. You can also show the R square, but then we said that we want to fit a cubic line, right? A cubic. This is the cubic line, and then this is the result. This is exactly the same as what we calculated over here. And let's uncheck this linear. We can even do 4th degree polynomial, right? Even higher, 9th degree, right? So spline interpolant, I don't know what that means, but this is another way to show to calculate the polynomial, right? So let's do it, for example, linear and cubic, right? So show the equation. And then you could also show the residues, which is sort of the error comparing the fitted line and the raw data. So you can use a bar plot, right? So the bar here, this is going to show you the different ways of the residues, right? Different magnitude of the residue. So if you use the linear fitting, right? So you can see that before this point, the linear, the line here is above the data point. So the error is the error value. The error is going to be data value minus the fitted line value, which is negative, right? When you get to here, it's positive, and then later on, it's negative again. But if you show the residue of the cubic fitting, right? So it's going to be much smaller. Right? So these are different ways to like interacting ways show you how the fitting result looks like for the polynomials. And as I said, they don't have to be polynomial. So in that situation, you can just type in the CF tool, right? CF tool stands for curve fitting tool. So now this is going to be a more, I would say, blown up tool for fitting the equations. It could be normal distribution. It could also be the log normal distribution or the power law distribution, right? So y equals x squared, right? No, y equals e to the power of x, right? So these more sophisticated type of equations. So then you could select the data, for example, fit name. You could call it TCP, right? X data being temperature, Y data being CP, right? So you can close. So it's going to first give you a polynomial, but we can also assume it's to be a different set of equation, right? So for example, you're selecting polynomial here, but then it could be exponential, right? Exponential, we know that it's not going to fit really well because exponential is always increasing. This one looks like it's going to taper off, right? So it could be Fourier, right? Fourier, the type of equation, right? Cosine and sine, right? So this is a better fit. It looks, at least looks a little bit better. And then the Gaussian fit, right? So we said it could be a Gaussian distribution, right? So then it's going to give you the mean value, the standard deviation, prefactor in front of the Gaussian distribution. Actually, there are even more, like the power distribution, right? A equals x to the power of b, right? The b doesn't, polynomial means that the b has to be integer, but here you don't have to be integer in terms of the power for the x, right? So the power fitting, rational fitting. So some of them are not going to fit really well. Sum of sine, right? So there are all different types of, let's say, the fitting tools. And this is basically way more than the polynomial fitting that we showed earlier, right? So you can also find out the factors here and the R square and so on and so forth. Okay, so this is the interactive curve fitting tools. So that's it for the curve fitting. So this class, we talked about the interpolation and curve fitting, right? So the difference is that interpolation, we're saying that the data points we get are real, and we're trying to find out the data in between these real data points, right? So then we talked about the linear interpolation, cubic spline interpolation. These are the two most commonly used ones, right? So the next is curve fitting, which is assuming that the data points are subject to error. So that's why we're trying to find out the underlying mechanism, underlying equation under the data point. So we're doing different types of regression, right? Linear regression, polynomial regression, other regression by using the CF tool, right? So this is interactive curve fitting tool. We also talk about the regression, linear regression, when we have to force certain line go through the 0, 0 point, right? So then we use the left division method from the matrix calculation, right? So yeah, I would say that's it for the regression, right? So we talk about the interpolation and curve fitting in this class. So this is, I would say, going to be quite helpful when we're trying to deal with engineering data, right? And then also trying to design our own systems. Okay, so that's it for this class, and let me know if you have any questions.